Have you ever tried to picture nothingness? Not just empty space, but true nothing. A complete void where even the concept of existence fades away. It turns out, according to our best understanding of physics, such a state might not even be possible. Because at the very smallest scales imaginable, far beyond the reach of our most powerful microscopes, the fabric of spacetime itself is alive with a seething, turbulent activity. Scientists call this phenomenon quantum foam, and it's one of the most radical ideas to ever emerge from theoretical physics. Think of it as a bubbling, effervescent ocean at the foundation of reality, where space and time are not smooth and continuous but fluctuate wildly, popping in and out of existence in a froth of raw potential. What makes quantum foam so extraordinary is how it challenges everything we think we know about the universe. We're used to living in a world of certainty, solid ground beneath our feet, predictable orbits of planets, the steady tick of time. But down at this unimaginably tiny scale, certainty breaks down. Particles wink into being only to vanish moments later. Wormholes may spontaneously form and collapse. Even the laws of cause and effect begin to blur. It's a domain where the very rules of reality are rewritten, and it forces us to question not just how the universe works, but what it even means for something to be real. This isn't science fiction, it's the frontier of human knowledge, and it's every bit as strange as anything we could dream up. In this video, we're going to explore 30 incredible theories about quantum foam, each one a window into this mysterious, chaotic foundation of the cosmos. Some of these ideas might sound unbelievable. Others could reshape our understanding of physics forever. We'll look at how quantum foam might influence the behavior of black holes, how it could hold the key to time travel, and why some scientists believe it might even connect parallel universes. This is a journey to the very edges of science where imagination and evidence meet. So settle in, open your mind, and get ready to dive into the foam, the hidden heart of reality itself. To truly grasp the bizarre nature of this quantum foam, we need to go back to the very idea that started it all. In the mid-1950s, a visionary physicist named John Archibald Wheeler looked at the two great pillars of modern physics: Einstein's general relativity, which describes the grand curvature of spacetime by mass and energy, and quantum mechanics, which governs the probabilistic, fuzzy behavior of the very small, and he asked a simple yet profound question. What happens when you apply the bizarre rules of the quantum world not to particles, but to the fabric of spacetime itself? His conclusion was that the smooth, predictable stage upon which the universe plays out simply cannot exist at the tiniest of scales. Wheeler realized that the famous Heisenberg uncertainty principle, which tells us we can never precisely know both a particle's position and its momentum at the same time, must also apply to the geometry of the universe. This means that at distances as unimaginably small as the Planck length, that's a decimal point followed by 34 zeros and then a 1 meters, the very concepts of here and there, of before and after, become fundamentally blurred. Space and time can no longer be measured with infinite precision. Instead, they are subject to violent, unpredictable fluctuations. In this realm, the smooth geometry of Einstein's universe is replaced by a seething, chaotic froth. Imagine trying to look at the surface of an ocean with a microscope powerful enough to see individual water molecules. The calm, flat surface would vanish, replaced by a turbulent, churning chaos. That is the essence of Wheeler's geometric fluctuation model. The universe isn't just made of particles, its very stage is built from a bubbling, effervescent foam of possibility. And it's this concept of a blurred, uncertain reality that brings us to our second mind-bending theory. If Wheeler's model shows us that spacetime is turbulent, then this next idea takes that turbulence and elevates it to a truly cosmic scale. This theory proposes that the quantum foam isn't just a chaotic froth, it is in fact a quantum superposition. Now, you might have heard of superposition in the context of Schrödinger's famous cat, which is both alive and dead until someone opens the box. Apply that same bizarre logic not to a particle or a feline, but to the entire structure of the universe itself. This suggests that at its most fundamental level, space-time does not have a single defined geometry. Instead, it exists in a blurred state of all possible configurations simultaneously. Every possible curvature, every potential connection between points, every conceivable timeline is superimposed upon one another in a dizzying tapestry of what-if. Think of it like this. Imagine you're looking at a single, perfectly still frame of a movie. That's the smooth, classical universe we perceive. But what if you could see all the frames at once, every possible shot the director could have taken, every alternate angle and edited out scene, all flickering and overlapping on the same screen? That overwhelming, chaotic collage is a closer analogy to what the quantum foam might actually be. It's a state where a wormhole could simultaneously be open and closed, where 2 points in space could be both adjacent and light years apart, and where the flow of time could be forward, backward, or not flowing at all. The universe at this scale doesn't have a single history. It has every history all happening at once. This resolves into the smooth, predictable continuum we experience through a process known as decoherence. When we, as large, macroscopic observers, interact with this foam, we effectively force it to choose. It's like trying to measure the exact position of a hummingbird's wings with your naked eye. All you see is a blur. But if you use a high-speed camera, you freeze one specific frame. Our act of observation, and indeed the interaction of all the particles within the universe, acts as that camera, causing this infinite superposition of possibilities to collapse into one coherent, measurable reality. So the calm spacetime we take for granted isn't the fundamental state. It's the averaged-out, large-scale result of an underlying reality that is infinitely more rich, complex, and strange. We are living in the aftermath of a constant, invisible collapse, a consensus reality built upon a foundation of endless possibility. If the idea of a blurred, superposed spacetime seems strange, then the next theory takes that strangeness and gives it a terrifyingly concrete form. Stephen Hawking looked at John Wheeler's quantum foam and saw not just a froth of geometry, but a seething sea of real, tangible structures. He proposed that the foam is not merely an abstract fluctuation, but is actually made of an unimaginable number of tiny, fleeting black holes and wormholes that constantly pop into and out of existence. These aren't the massive, star-devouring black holes we know from astronomy. These are quantum black holes smaller than a single atom and lasting for only a fraction of a second. In this model, the fundamental building blocks of reality itself are the most extreme objects the universe can create. Think of the vacuum of space not as empty, but as a kind of cosmic carbonated drink. The bubbles fizzing to the surface are analogous to these virtual black holes. Each one is a tiny, self-contained universe with its own event horizon, born from the raw energy of quantum fluctuations. According to the rules of quantum mechanics, empty space is never truly empty. Particle-antiparticle pairs are constantly appearing and almost instantly annihilating each other. Hawking suggested that sometimes these fluctuations can be so intense, they warp spacetime enough to pinch off into a microscopic black hole. It forms, exists for a fleeting moment, and then evaporates away in a burst of energy, all before it could ever be directly observed. This endless cycle of creation and destruction is what we perceive as the smooth fabric of space. This radical idea offers a potential key to unlocking one of the greatest mysteries in modern physics, the black hole information paradox. A large black hole evaporates over eons by emitting what we call Hawking radiation. But this radiation appears to be completely random, carrying no information about the material that fell in. This suggests that information is fundamentally destroyed, which violates a core principle of quantum mechanics. Hawking's virtual black hole foam might provide a solution. If spacetime is permeated by these tiny, short-lived black holes and their connecting wormholes, information that falls into a large black hole might not be lost forever. Instead, it could be secretly transferred, scrambled, and eventually released back into the universe through the complex, interconnected network of the foam. The information isn't destroyed, it's just encoded into the fundamental structure of reality itself, hidden within the foam's chaotic churn. This concept pushes our understanding to the absolute limit, suggesting that the universe is built upon a foundation of perpetual collapse and rebirth. It transforms the vacuum from a passive stage into an active, dynamic participant in the laws of physics, where the most extreme phenomena are not rare astronomical events, but the very essence of existence at the smallest scale. But if spacetime is truly this chaotic foam of virtual black holes and superposed geometries, how could we ever hope to study it in a rigorous mathematical way? We can't peer directly at the Planck scale, and the mathematics of blending general relativity with quantum mechanics often leads to infinities and dead ends. This challenge led a group of physicists to take a radically different approach. Instead of trying to force the two theories together with equations, they asked, what if we build a universe from the ground up? This is the core idea behind causal dynamical triangulations, a theory that treats the fabric of spacetime not as a continuous sheet, but as a vast mosaic of unimaginably tiny, simple pieces. Imagine you're an artist trying to sculpt a perfectly smooth, curved statue. You wouldn't start with a giant, formless block of marble. Instead, you might build a rough framework out of simple, straight metal rods, welding them together into a complex wireframe. The more rods you use and the smaller they are, the closer your framework approximates the ideal smooth curve of the final sculpture. Causal dynamical triangulations applies this same logic to the universe itself. The fundamental building blocks aren't rods, but tiny, four-dimensional triangular pieces called simplices. Each one is a basic geometric shape, and the theory dictates strict causal rules for how these pieces can connect to one another. They must fit together in a way that preserves the proper sequence of cause and effect. A future event can never influence a past one, even at this microscopic level. Now, here is where the magic happens. When researchers run massive computer simulations, connecting billions upon billions of these tiny triangular pieces according to these causal rules, something extraordinary emerges from the chaos. Without being programmed to do so, this frantic, jumbled network of simple shapes spontaneously self-organizes. It condenses into a clear, stable, four-dimensional structure that looks exactly like the smooth, continuous spacetime we observe in our large-scale universe. It's as if you tossed a colossal bag of Legos into the air, and they fell to the ground already assembled into a perfectly detailed model of a starship. From a lower-dimensional, foamy substrate of infinite possibilities, a single, coherent reality crystallizes. This result is staggering. It suggests that our familiar four-dimensional world 3 of space and 1 of time is not a fundamental given. It is an emergent property, a large-scale illusion born from the collective behavior of countless tiny, chaotic parts. The smooth stage upon which galaxies dance and life evolves is at its heart a statistical average, much like the smooth surface of a pond is the average effect of countless jostling water molecules. Causal dynamical triangulations provides one of the most compelling and computable frameworks for quantum gravity because it doesn't just describe the foam, it actually constructs it from first principles and shows us, step by digital step, how our magnificent universe can arise from such a tumultuous beginning. While causal dynamical triangulations build spacetime from tiny geometric pieces, another profound theory suggests the universe is not just assembled from parts, but is fundamentally woven from a web of relationships. This is the realm of loop quantum gravity, which proposes that space itself is not continuous but is instead composed of finite, indivisible quanta. imagine the digital display you're watching this on. From a distance, the image appears smooth and continuous, but up close, you can see it's actually made of individual pixels. Loop quantum gravity argues that the universe operates on a similar principle, just at a scale a trillion times smaller. At the heart of this theory are structures called spin networks. Think of a spin network not as a physical object floating in space, but as space itself. It's a vast, abstract web where the threads or links represent the smallest possible units of area, and the points where they connect, the nodes, represent the tiniest quanta of volume. There is no space outside of this network. This web is the very fabric of the cosmos. The spin part refers to a quantum property associated with each link, which determines the precise size of the area quanta it represents. In this model, the quantum foam isn't a chaotic, formless froth. It is this exact network, this intricate tapestry of quantized geometry, constantly evolving and changing. This leads to a breathtaking implication. There is a literal, smallest possible piece of space. You cannot divide a volume or an area past a certain point because you would run out of nodes and links in the spin network to subdivide. This is a direct solution to the problem of infinities that plague other theories of gravity. In Einstein's general relativity, the center of a black hole is a point of infinite density called a singularity, a clear sign that the theory has broken down. But in loop quantum gravity, such a singularity is impossible. You simply cannot compress matter and energy into an infinitely small point because space itself comes in finite, indivisible chunks. Matter can only be compressed so far before it meets the fundamental graininess of spacetime, a finding that suggests black holes might not be eternal prisons but could instead transform into something else entirely, a concept we'll explore in more detail later. So, in this framework, the quantum foam is a highly ordered yet dynamic structure. It's not random noise, it's a cosmic code, a network of relationships from which everything, the dimensions of space, the passage of time, and the matter within it ultimately emerges. The smooth, continuous space we move through is a direct result of this underlying pixelation. Much like a flowing digital video emerges from the rapid refresh rate of its individual pixels. Loop quantum gravity gives us a universe that is not just built on quantum foam, but is quite literally made of it, a vast and evolving computation of geometric information. This mind-bending concept leads us to one of the most radical and profound theories on our list, an idea that suggests everything we perceive as reality might be nothing more than an elaborate cosmic projection. This is the holographic principle, and when applied to the quantum foam, it proposes that the frothing, chaotic microstructure of spacetime is not the fundamental layer of reality at all, but a three-dimensional illusion. All the information needed to describe every star, every planet, and every one of us is actually encoded on a distant, two-dimensional surface that surrounds the universe, like the information etched onto the surface of a holographic film. The name comes from a real-world hologram where a three-dimensional image is reconstructed from a flat, two-dimensional piece of film. Scratch the surface of the film, and you don't just damage one part of the 3D image, the entire picture becomes slightly fuzzier. This demonstrates that the information for the whole is distributed across every part of the surface. The holographic principle argues our universe operates in exactly the same way. The events happening here in the volume of space around you are not entirely local. They are linked to and defined by information stored on a vast cosmic boundary we cannot see. This revolutionary idea first gained serious traction from the study of black holes. Stephen Hawking showed that when matter falls into a black hole, the information about that matter isn't necessarily lost. Instead, it might be smeared out and encoded across the black hole's event horizon, its two-dimensional point of no return. The entire three-dimensional interior of the black hole, with all its mysterious contents, could be described by the information on its two-dimensional surface. The holographic principle boldly asserts that what is true for a black hole is true for the entire cosmos. Our universe itself might be a kind of black hole interior, with its information boundary existing at the very limits of the observable universe. So, what does this mean for the turbulent quantum foam we've been discussing? If the holographic principle is correct, the foam might be a secondary effect, a kind of pixelation or noise that emerges from the process of translating a fundamentally two-dimensional reality into the three-dimensional world we experience. The seething virtual particles, the fleeting wormholes, the blur of superposed geometries, all of it could be the projected image, while the true, fundamental activity is happening on that flat, distant boundary. The foam is the flicker on the movie screen, while the real story is contained on the film strip itself. This radically alters our understanding of the universe's information capacity. In a classical, three-dimensional view, the amount of information you can pack into a region of space is limited by its volume. But if the universe is a hologram, the true limit is defined by the area of its boundary. This implies a profound and counterintuitive fact. The maximum information possible in your living room is not proportional to the size of the room itself, but to the surface area of its walls. There is a fundamental finiteness to reality, a limit to the complexity and detail the universe can contain, and it is determined by a surface we will likely never see or touch. The quantum foam, in this view, is the visual manifestation of this ultimate information limit, the graininess of reality reminding us that we are living inside a projection, a cosmic hologram of unimaginable complexity and beauty. Yet another perspective on the quantum foam emerges from one of the most ambitious projects in all of theoretical physics, string theory. This framework seeks to be a theory of everything, proposing that the fundamental constituents of the universe are not point-like particles but unimaginably tiny, vibrating strings. And in the string theory view, the quantum foam isn't just a froth of space-time, it's a symphony of these strings playing out in a universe with far more dimensions than we can see. We experience the world in three spatial dimensions and one of time. String theory, however, requires extra dimensions for its mathematical consistency, often proposing a total of 10 or 11. So where are these other dimensions? The theory suggests they are compactified, or curled up into a space so incredibly small that they are hidden from our perception. The shape of these hidden dimensions is absolutely critical. It determines everything from the masses of particles to the strength of the forces that govern them. And the most promising candidates for these shapes are intricate multi-dimensional forms known as Calabi-Yau manifolds. Imagine a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but if you get very close, you see the hose has a second dimension, its circular circumference. In string theory, our entire three-dimensional universe could be like that long dimension of the hose, while the 6 extra dimensions are curled up into a complex Calabi-Yau shape, a structure far too small for us to detect directly. The properties of this shape dictate how the strings within it can vibrate, and since, in this theory, the different vibrations of a string are what give rise to different particles, an electron, a photon, a quark, the geometry of these hidden dimensions literally writes the laws of physics for our visible universe. So, how does this connect to the seething quantum foam? In this model, the foam is the manifestation of strings interacting at the Planck scale. The wild fluctuations of spacetime are not just random geometric noise, they are the result of strings stretching, splitting, and merging with one another. The fleeting wormholes and virtual black holes could be explained by specific string configurations, perhaps one string forming a loop around a tiny, compactified dimension, pinching off a piece of spacetime in the process. The foam's chaotic nature is a direct result of the string's quantum vibrations and their dance through these extra dimensions. The shape of the Calabi-Yau space is therefore the master architect of the foam. A slightly different manifold would lead to a different pattern of vibrational possibilities for the strings, which would in turn create a quantum foam with entirely different properties. This would produce a universe with different fundamental constants and forces, a universe where atoms might not even form. This idea provides a potential mechanism for the existence of a multiverse, a vast landscape of universes, each with its own unique Calabi-Yau geometry, its own unique set of physical laws, and its own unique flavor of quantum foam bubbling beneath the surface. Our universe, with its particular foam and its specific laws, would be just one possibility in an infinite cosmic array. This brings us to a theory that pushes the very idea of geometry to its absolute breaking point. We've explored models where spacetime is built from pieces woven from a spin network or projected from a hologram. But what if, at the most fundamental level, the very concept of a point in space loses all meaning? This is the radical proposition of non-commutative geometry, a theory suggesting that the quantum foam is not just fuzzy or pixelated, it is a realm where the traditional rules of geometry and measurement simply cease to apply. To grasp this, we need to revisit a cornerstone of quantum mechanics, the Heisenberg uncertainty principle. We're familiar with its implication for particles, that you can't know both their exact position and exact momentum at the same time. Non-commutative geometry applies this same fundamental uncertainty not to particles, but to the coordinates of spacetime itself. In our everyday world, measuring things in a different order doesn't matter. You can measure the length of a table and then its width, or its width and then its length, and you'll get the same result. The operations commute. But at the Planck scale, this theory proposes that measuring one spacetime coordinate interferes with the measurement of another. The act of pinpointing a location in the x direction fundamentally alters what you would find in the y or z direction. The order of measurement matters immensely. This means you could never construct a perfectly precise, infinitely small point in space, because the very act of trying to measure its position would make its position uncertain. Spacetime becomes inherently fuzzy, like a photograph where the very act of focusing on one detail causes another to blur. This isn't a limitation of our instruments, it's a fundamental property of the universe. The smooth, continuous coordinate grid we use to navigate the world dissolves into a probabilistic, foamy soup where precise locations are impossible to define. So if traditional geometry, which is built on the idea of well-defined points and distances, breaks down what takes its place, this is where the non-commutative part of the name comes in. The theory replaces the familiar concept of a geometric space with a more abstract algebraic structure. Think of it like this: instead of describing a circle by plotting all the points that are an equal distance from a center, a geometric definition, you could describe it by the algebraic equations that all those points satisfy. The algebra captures the essence of the shape without ever needing to refer to a specific point. Non-commutative geometry argues that the true description of spacetime at the quantum level is this algebra of non-commuting coordinates. The foam is not a set of points. It is a web of relationships and operations where the classical idea of here and there is replaced by a complex mathematical symphony of interconnections. This abstract framework offers a powerful new way to unify the forces of nature. In this model, the wild fluctuations of the quantum foam, the flickering wormholes and virtual black holes, can be seen as direct consequences of this non-commutative algebra. The forces we experience, like gravity and electromagnetism, might not be fundamental at all, but merely emergent properties of this deeper geometric uncertainty. The foam isn't just the backdrop for physics. Its fuzzy, non-commutative nature could actually be the source of physics itself, generating the laws and forces that govern our universe from a realm where location is never certain, and the very landscape of reality is in a constant state of quantum negotiation. What if gravity, the force that holds planets in orbit and gives us weight, isn't a fundamental force at all? What if it's merely a side effect, an illusion generated by something much deeper? This is the radical proposition of physicist Eric Verland's theory of entropic gravity. It suggests that the smooth stage of space-time and the force we call gravity do not exist as primary entities. Instead, they emerge from the statistical behavior of microscopic components, much like the pressure of a gas emerges from the collective jostling of countless molecules. In this view, the quantum foam isn't a seething froth of geometry, it's a statistical fluctuation in a vast underlying network of information. To understand this, we need to reframe our concept of the most mysterious and alluring objects in the universe, black holes. The key lies in a famous thought experiment. Imagine slowly lowering a box of particles toward a black hole's event horizon. Just before it crosses the point of no return, you manage to retrieve it. Thermodynamics tells us that this process must result in a change in entropy, a measure of the disorder or information content of a system. The work you did to lower and retrieve the box is directly related to a change in the black hole's entropy. This deep connection between gravity, energy, and information led Jacob Bekenstein and Stephen Hawking to discover that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This was a huge clue that the fundamental description of a region of space might reside on its boundary, not within it. Verland took this idea and ran with it. He proposed that what is true for a black hole is true for the entire universe. Gravity, he argues, is not a force that pulls objects together. It is an entropic force. It emerges because systems naturally evolve toward states of higher entropy or disorder. Think of it like this. If you place a rubber duck in a bathtub, it will drift to the side. It isn't being pulled by a fundamental bathtub force. It moves because that position maximizes the disorder of the entire system. The water molecules can explore more possible configurations with the duck out of the way. Verland's astonishing claim is that gravity works the same way. A planet moves around a star not because it's being pulled by the star's gravity, but because that path is the one that maximizes the entropy of the underlying microscopic degrees of freedom of spacetime itself. So, what are these microscopic degrees of freedom? This is where the theory connects directly to the quantum foam. Verland suggests that spacetime is built from a vast network of entangled quantum bits or qubits of information. The quantum foam, with its wild fluctuations and fleeting structures, is the visible manifestation of this network's statistical behavior. The seething foam isn't the cause of gravity. It is the thermal noise, the jittering of the fundamental information, bits from which gravity and spacetime themselves emerge. The foam is the thermodynamic engine of reality. This perspective radically redefines our place in the universe. We are not living on a smooth, pre-existing geometric stage. We are living within a dynamic, holographic display that is constantly computing its own existence. The force that grounds us is not a fundamental interaction but a statistical tendency, a collective urge toward disorder that manifests as attraction. It suggests that at its heart, the universe is not made of stuff but of information. The laws of physics are not written in stone. They are the emergent byproducts of an immense, complex system processing data on a cosmic scale. The quantum foam, in this entropic view, is the visual static on the screen of reality, reminding us that we are witnessing the output of a computation whose true workings are hidden in a deeper, informational layer of the cosmos. This brings us to a theory that challenges our most fundamental experience of reality, the steady, irreversible flow of time. All the models we've explored, from virtual black holes to spin networks, must eventually confront the problem of time itself. In our macroscopic world, time's arrow seems undeniable and absolute. Coffee cools, eggs break, and we grow older, always moving from a defined past toward an uncertain future. But when we descend into the quantum foam, this reliable, one-way street may completely vanish. Some of the most profound theories in physics suggest that time, as we know it, is not a fundamental feature of the universe but a large-scale illusion that emerges from the timeless chaos of the Planck scale. To understand why, we need to look at the two great pillars of physics. Quantum mechanics, which governs the very small, is fundamentally reversible. The equations that describe how a particle moves from point A to point B work just as well if you run the film backward. There's nothing in the math that dictates a preferred direction of time. On the other hand, thermodynamics, which governs systems with many particles, gives us the second law. Entropy, or disorder, always increases, creating the irreversible arrow of time we all experience. The universe is caught between these two conflicting descriptions. The quantum foam exists at the precise boundary where they meet, and it's here that the concept of time becomes profoundly fuzzy. In the seething foam of virtual black holes and wormholes, causality itself breaks down. An event that we would label as a cause and its subsequent effect can become blurred. A wormhole might momentarily connect a point in what we call the future to a point in what we call the past, making the very sequence of events meaningless. At this scale, the universe doesn't have a single flowing timeline. It has every possible timeline, a vast superposition of all potential sequences of events existing simultaneously. In this realm, asking what happened first might be as meaningless as asking which single water molecule in a wave crashed onto the shore first. The wave is a collective behavior, not a story of individual molecules. This is where theories like causal dynamical triangulations, which we discussed earlier, provide a crucial clue. Recall that the simulation only produced a stable, four-dimensional universe when the tiny geometric pieces were connected with strict causal rules that preserved the order of cause and effect. This suggests that the arrow of time we experience isn't an illusion, but it is an emergent property. It arises from the collective organization of countless timeless, causality-free quantum events. The smooth flow of time is the thermodynamic average of a fundamentally atemporal system, much like the smooth pressure of a gas emerges from the chaotic, directionless motion of individual molecules. The profound implication is that the past, present, and future might not be sequential in any fundamental way. Physicists like Julian Barber have proposed that the universe is a vast landscape of static, timeless nows, which he calls time capsules. Our conscious experience, our feeling of moving through time, is a result of our brain processing a sequence of these static states, each one containing the appearance of a record memories, fossils, light from ancient stars, that creates the compelling illusion of a past. In this view, the quantum foam is the generator of all possible nows, and the emergent arrow of time is the path we take through this eternal landscape. This presents a monumental challenge for cosmology. If time is not fundamental, how do we describe the origin of the universe? The Big Bang is often described as the beginning of space and time. But if time is emergent, the Big Bang wasn't a beginning in time. It was the moment when time itself, as a property of our universe, first crystallized out of the timeless quantum foam. The question, what came before the Big Bang, might be a category error, like asking what is north of the North Pole. There was no before, because the framework of before and after did not yet exist. Our entire cosmic history, from the first instant to the present day, could be a single, frozen structure within a timeless multiverse, and we are simply unfolding it moment by moment along an axis we have invented and called time. If the timeless nature of the quantum foam challenges our perception of reality, its potential connection to the universe's most dominant force is even more staggering. We now arrive at a hypothesis that links the smallest possible fluctuations in the vacuum to the largest scale behavior of the cosmos. This is the proposed connection between quantum foam and dark energy, the mysterious force causing the expansion of the universe to accelerate at an ever-increasing rate. The idea is both elegantly simple and profoundly problematic, leading us directly to what many physicists call the worst prediction in the history of science. The logic begins with what we've already established. Empty space is not empty. The quantum foam is a seething cauldron of virtual particle pairs constantly blinking in and out of existence. According to quantum field theory, each of these fleeting fluctuations carries a tiny amount of energy. When you add up all this activity happening in every single cubic centimeter of what we perceive as a vacuum, you get what is known as vacuum energy or zero-point energy. This isn't just a theoretical curiosity. Its effects have been measured in the lab through phenomena like the Casimir effect, where two metal plates placed incredibly close together in a vacuum are gently pushed toward each other by the pressure of these virtual particles outside the plates. Now take this concept of vacuum energy and apply it to the entire universe. Every tiny volume of space, from the void between galaxies to the emptiness in the room around you, is brimming with this fundamental energy. According to Einstein's theory of general relativity, energy, all forms of energy, has a gravitational effect. This vacuum energy should therefore be exerting a gravitational pull on the cosmos. But here's the twist. While normal matter and energy create attractive gravity that pulls the universe together, a constant, pervasive energy woven into the fabric of spacetime itself would produce a repulsive form of gravity, a kind of negative pressure that pushes spacetime apart. This is precisely the effect we observe from dark energy. So the theory seems beautifully elegant. The quantum foam's vacuum energy is dark energy. The chaotic churn at the Planck scale is the engine driving the accelerated expansion of the entire universe. This is where we encounter the infamous cosmological constant problem, a discrepancy of such monumental proportions that it threatens to undermine the entire idea. The problem is one of scale. To calculate the theoretical value of this vacuum energy, physicists sum up the contributions from all possible quantum fields across all possible energy levels right up to the Planck scale. When they do this math, the result is an energy density of around 10 to the 112 joules per cubic meter. This is an unimaginably huge number. Now compare that to the value for dark energy we actually observe through astronomical measurements of the universe's expansion. The observed value is about 10 to the negative 9 joules per cubic meter. The theoretical prediction is a staggering 120 orders of magnitude. That's a number with 120 zeros after it, larger than the observed value. If the theoretical prediction were correct, the repulsive force of this vacuum energy would have been so immense that it would have ripped every atom, every nucleus, every fundamental particle in the universe apart within a fraction of a second after the Big Bang. Stars, planets, and life could never have formed. The fact that we exist to even ponder this question is proof that the prediction is catastrophically wrong. This isn't just a small error in calculation. It's the largest discrepancy between theory and observation in all of science. It suggests we are fundamentally misunderstanding something critical about the relationship between the quantum world and gravity. One potential solution is a form of cosmic fine-tuning or a cancellation mechanism of unimaginable precision. Perhaps the contributions from different quantum fields and particles somehow cancel each other out, leaving behind only a tiny, leftover residue that we now measure as dark energy. But this requires a level of fine-tuning that seems unnatural to most physicists. It would be like balancing a pencil on its tip for billions of years in a hurricane. Other theories propose more radical solutions. Perhaps the vacuum energy is not constant but dynamic, changing over the lifespan of the universe. Or maybe our understanding of gravity is incomplete on the largest scales, and dark energy is not an energy at all but a sign that Einstein's theory of general relativity needs to be modified. The holographic principle we discussed earlier offers another fascinating possibility. If the information content of a volume of space is actually determined by its surface area and not its volume, then the true vacuum energy might be vastly smaller, as it would be spread across a boundary rather than filling a bulk. This could naturally resolve the discrepancy, pointing once again to the idea that our three-dimensional reality is a projection from a two-dimensional source. The quantum foam in this view might be the holographic grain, and its energy is not the colossal sum we calculate, but the faint echo of a far more fundamental process happening at the edge of the universe. But if the quantum foam's structure is so chaotic that it defies traditional geometry, could it also alter the very constants we rely on to understand the cosmos? For over a century, one principle has been a bedrock of modern physics, the constancy of the speed of light. According to Einstein's special relativity, the speed of light in a vacuum is the universe's ultimate speed limit, an unchanging constant denoted by c that is the same for all observers regardless of their motion or the light's energy. This principle, known as Lorentz invariance, underpins much of our theoretical framework. Yet, a fascinating class of theories suggests that the quantum foam might create tiny, subtle cracks in this seemingly immutable foundation, causing light speed to vary ever so slightly based on its energy. The reasoning is remarkably intuitive when you picture the foam's nature. Imagine two runners trying to cross a field. One is a marathoner on a smooth, paved track. The other is a trail runner navigating a rocky, uneven path full of potholes and obstacles. Even if they are equally fit, the trail runner will be slightly slowed and jostled by the rough terrain. Now apply this analogy to light. A photon is not just a particle, it's a ripple in an electromagnetic field traveling through the medium of spacetime. If spacetime at the Planck scale is a turbulent foam of virtual black holes and wormholes, it isn't a smooth track, it's the ultimate cosmic trail run. A very low-energy photon, like a radio wave, might be too long to notice these microscopic bumps. It would effectively experience an averaged-out, smooth spacetime. But an incredibly high-energy photon, like a gamma ray, has a much smaller wavelength. It could, in theory, interact with the individual lumps and bumps of the foam itself, feeling every virtual black hole and quantum fluctuation along its path. This interaction would cause it to effectively travel a slightly more tortuous path, slowing it down by a minuscule amount compared to its lower energy cousins. This idea, often called foam-induced vacuum dispersion, suggests that two photons of different energies, emitted at the exact same instant from a cataclysmic event billions of light years away, could actually arrive at our telescopes at detectably different times. The higher energy photon would be the trail runner, arriving a fraction of a second later than the marathoner. The challenge, of course, is that the scale of this effect is unimaginably small. The foam's structure operates at the Planck length, so the expected time difference over a vast cosmic distance might be mere milliseconds. Detecting such a tiny delay requires the perfect natural laboratory, gamma-ray burst. These are the most violent explosions in the universe since the Big Bang, unleashing a furious flood of light across the entire spectrum, from low-energy radio waves to ultra-high-energy gamma rays, all in a blindingly short flash. They are the ideal cosmic stopwatch. For decades, physicists have been using observatories like the Fermi Gamma Ray Space Telescope to meticulously analyze the light from these distant bursts. They search for a telltale energy-dependent lag in the arrival times of the photons. A confirmed detection would be nothing short of revolutionary. It would provide the first direct experimental evidence for the existence of quantum foam and would immediately falsify strict Lorentz invariance, forcing a major rewrite of Einstein's theory of special relativity. It would prove that spacetime is not a smooth, classical continuum, but has a granular, foamy structure that light must navigate. The implications would ripple through all of physics, offering crucial experimental guidance to theories like loop quantum gravity and string theory, which predict different types of foam-induced effects. Yet, despite intense searching, no such lag has been conclusively found. The speed of light continues to appear constant, even across billions of light years. This null result is in its own way profoundly informative. It places incredibly stringent constraints on the possible models of quantum gravity. It tells us that if the foam exists, its structure must be far more subtle and uniform than some of the wilder models suggest. Perhaps the foam's fluctuations are correlated in a way that preserves an average smoothness, or maybe Lorentz invariance is an emergent symmetry that holds perfectly at our energy scales, even if it's broken at the Planck level. The continued, unwavering constancy of C is a silent but powerful message from the universe, challenging theorists to build models of quantum foam that are not just strange, but also elegantly consistent with the stubborn resilience of light's cosmic speed limit. But the bizarre implications of the quantum foam don't stop at the speed of light. They reach right up to the precipice of the most terrifying objects in the cosmos, forcing us to confront a paradox so severe it threatens to unravel our understanding of black holes. This is the infamous firewall paradox, and it suggests that the event horizon of a black hole, rather than being an invisible point of no return, might be a seething wall of pure energy, a literal death trap for anything that falls in. And the potential source of this cosmic inferno might be the very quantum foam we've been exploring. To understand the paradox, we need to revisit two fundamental principles that have long been cornerstones of physics. The first is the equivalence principle from general relativity, which states, in essence, that if you were falling freely into a black hole, you wouldn't feel anything special as you crossed the event horizon. There would be no dramatic warning sign, no sudden jolt, just the smooth, continuous curvature of spacetime. The second is the principle of unitarity from quantum mechanics, which asserts that information cannot be lost or destroyed. It can be scrambled, but it must be preserved. For decades, physicists believed these two principles could coexist peacefully thanks to a concept called black hole complementarity, inspired by the wave-particle duality of quantum mechanics. This idea suggested that from the perspective of an outside observer, information is smeared across the event horizon and slowly released via Hawking radiation, while from the perspective of someone falling in, the information travels intact into the black hole's interior. Both views could be simultaneously correct. They were just complementary descriptions of the same reality, with no single observer able to see both versions at once. It was an elegant, if strange, solution. The firewall paradox shatters this delicate truce. In 2012, a group of physicists including Ahmed Olmary, Donald Maroff, Joe Polchinski, and James Sully, often referred to by the acronym AMPS, performed a detailed thought experiment. They asked what would happen to the information of an object falling into a black hole if we insist that information is not lost. Their calculation led to a shocking conclusion. For information to be preserved and eventually radiated back out, the Hawking radiation particles leaving the black hole must be intricately entangled with particles that fell in earlier. But for the infalling observer to have a smooth experience crossing the horizon, they must also be entangled with those same Hawking particles. This creates a catastrophic problem known as the monogamy of entanglement, a fundamental quantum rule that says a particle cannot be maximally entangled with two different systems at the same time. This quantum love triangle is impossible to resolve. If the information is to be saved, the entanglement must be transferred to the outgoing radiation, violently severing the connection between the inside and outside of the black hole right at the horizon. This break would unleash an enormous amount of energy, transforming the event horizon from a smooth mathematical surface into a blazing curtain of high-energy particles, a firewall that would instantly incinerate any astronaut daring to cross it. The equivalence principle would be brutally violated. This is where the quantum foam enters the picture with a potential and deeply ironic solution. The intense gravitational energy at the event horizon of a black hole magnifies the fluctuations of the quantum foam to an extreme degree. The seething froth of virtual particles and wormholes isn't just a gentle background buzz here, it's a maelstrom of unimaginable violence. Some theories propose that this foamy turbulence could act as a kind of cosmic scrambler, violently mixing and encoding information from the infalling matter into the Hawking radiation long before it reaches the central singularity. The information isn't lost, it's just processed and disseminated through the chaotic foam at the horizon. In this view, the firewall might not be a sudden, sharp wall of fire, but a more diffuse and energetic manifestation of the foam itself. The infalling observer wouldn't hit a single, catastrophic barrier, but would instead experience a gradual transition into a region of such extreme quantum turbulence that the very concepts of particle and location break down entirely. The experience wouldn't be smooth, but it might not be an instantaneous death by incineration either. It would be a dissolution into the chaotic, information-scrambling froth that constitutes the true nature of the horizon. However, this foamy resolution comes with its own profound cost. It suggests that black hole complementarity, the idea that both the inside and outside views are valid, is an illusion we can only maintain from a safe distance. The intense foam at the horizon fundamentally decouples the interior of the black hole from the exterior universe. The inside and outside become causally disconnected not just by gravity, but by an impassable domain of quantum chaos. This doesn't just resolve the firewall paradox, it radically redefines what a black hole is. The event horizon is not a mere point of no return. It is a dynamic, active membrane of quantum computational activity, a boundary where information is processed and reality is fundamentally rewritten. The black hole is not a simple hole in space-time, but an object whose most important property is this frenetic, foamy surface where the laws of physics are stretched to their absolute limit. This leads us to one of the most significant and elegant proposals in modern cosmology, a theory that connects the most microscopic chaos directly to the largest structures we see in the sky. What if the entire cosmic web of galaxies, every cluster, every supercluster, every vast, empty void owes its existence to the faintest whispers in the quantum foam from the universe's very first instant? This is the profound idea that quantum foam fluctuations not only existed during the Big Bang, but actually provided the essential seeds for everything that followed, kickstarting a period of hyper-expansion known as cosmic inflation and ultimately determining the distribution of all matter. To understand this, we need to rewind to a time so early that the universe was a seething, hot, dense plasma where the energy was so immense that the quantum foam wasn't just a microscopic phenomenon, it was the dominant feature of reality. At these energies, the fluctuations of spacetime itself were violent and universal. According to the theory of inflation, a tiny patch of this primordial universe was caught in a peculiar state called a false vacuum, a high-energy configuration that possessed a bizarre property. It generated a powerful repulsive gravity, causing that patch to expand at an exponential rate, doubling in size every tiny fraction of a second. This period of inflation is what took a subatomic speck and blew it up to something larger than our entire observable universe in the blink of an eye, solving major puzzles like why the cosmos appears so uniform in every direction. But here's the critical part. Inflation needed a trigger to end, and it needed some form of imperfection to work with. A perfectly smooth, featureless universe would have expanded into a perfectly smooth, featureless void forever. It needed a blueprint, a set of initial wrinkles to amplify. This is where the quantum foam provided the essential ingredient, the same Heisenberg uncertainty that makes spacetime fuzzy at the Planck scale, guaranteed that this primordial energy field, known as the inflaton field, couldn't have a perfectly uniform value everywhere. Tiny, random quantum fluctuations were imprinted upon it, some regions having a slightly higher energy density, others slightly lower. These weren't caused by anything. They were the inevitable, fundamental uncertainty of the quantum world made real. As inflation stretched this tiny patch of space to a cosmic scale, it stretched these infinitesimal quantum wrinkles along with it, magnifying them from quantum fluctuations to astronomical density variations. The regions of slightly higher density, where the inflattened field held a bit more energy, had slightly stronger gravity. Over billions of years, these over-dense regions acted as gravitational anchors, pulling in surrounding matter, eventually collapsing to form the first stars, galaxies, and the vast filamentary structures we see in the universe today. The maps of the cosmic microwave background radiation, the afterglow of the Big Bang, show us this exact pattern of hot and cold spots, a direct snapshot of those magnified quantum seeds. The entire large-scale structure of the cosmos is therefore a fossilized imprint of the quantum foam's primordial turbulence. This concept naturally propels us into the staggering realm of the multiverse. If one tiny patch of false vacuum can inflate into our entire observable universe, what's to stop it from happening elsewhere? The theory suggests that the process could be eternal. In different regions of the primordial foam, the inflattened field would have randomly fluctuated into different values, each triggering its own separate bout of inflation and creating its own distinct universe with potentially different physical constants. Our universe, with its specific set of laws and its particular pattern of galaxies, would be just one bubble in a vast, ever-expanding cosmic foam of universes, each with its own unique history and properties, forever separated from us by the unimaginably rapid expansion of their own inflationary domains. Yet another approach to finding evidence for this frothy spacetime looks beyond photons to a far more elusive cosmic messenger, the neutrino. These ghostly particles with no electric charge and almost no mass barely interact with normal matter at all. Trillions are passing through your body every second, completely unnoticed. This aloofness, which makes them so difficult to detect, is precisely what could make them the perfect probes for the quantum foam. Because they so rarely bump into anything, their journey across the universe is almost entirely undisturbed by the matter they pass through. Any anomalies in their travel could therefore be a much cleaner signal of an interaction with the fabric of spacetime itself. Think of it like this: if you were trying to study the texture of a glass window, you could throw different things at it. Throwing a handful of mud would mostly just tell you about the mud, obscuring the details of the glass. But shining a pure, coherent laser beam through it would reveal subtle distortions, tiny scratches, waves, or impurities by how the light is affected. High-energy photons can be like that mud. Their electromagnetic nature means they interact with other matter and fields along their journey, adding noise to the signal. Neutrinos, by comparison, are that pristine laser beam. They fly in a nearly straight line from their cataclysmic sources, like supernova or active galactic nuclei, for billions of light years, making them ideal for testing if the vacuum they travel through is truly smooth. So, what would a neutrino see, or rather feel, as it traverses the quantum foam? One compelling idea is that the foam's chaotic structure would act like a subtle fog, causing extremely high-energy neutrinos to scatter. This wouldn't be a dramatic collision, but a slight deflection, a tiny jostle from its path due to an interaction with a virtual black hole or a space-time wormhole fluctuation. Over an immense cosmic distance, these tiny deflections could add up, potentially blurring the point of origin for the highest energy neutrinos we detect. Another possibility, similar to the photon delay, is a slight energy-dependent speed variation. A petaelectronvolt neutrino might arrive a fraction of a second later than its lower energy siblings from the same event. The hunt for these effects is underway at the most extreme laboratories on Earth. The Ice Cube Neutrino Observatory is a colossal detector buried deep in the Antarctic ice sheet. It uses a cubic kilometer of pristine ice as its detection medium, watching for the incredibly rare flash of blue light emitted when a neutrino does finally interact with an atom in the ice. By analyzing the directions and energies of neutrinos that have traveled across the universe, Ice Cube scientists can search for any statistical evidence of this foamy scattering. Meanwhile, instruments like the ANITA experiment, a radio antenna array carried by a high-altitude balloon over Antarctica, search for an even stranger signature. ANITA detects ultra-high-energy neutrinos that skid through the Earth and interact with the ice below, producing radio waves that travel upward. The trajectory of these particles is exquisitely sensitive to any minute deviation, offering another potential window into Planck-scale physics. While no definitive signal has been found yet, the mere possibility is a testament to how far our experimental reach has extended. We are now using particles that barely exist to probe a scale that is practically unreachable, searching for imperfections in nothingness itself. Each neutrino that arrives unscathed places tighter constraints on the wilder models of quantum foam, helping to guide theorists toward a more accurate picture of spacetime's true, fundamental nature. Yet this search for time delays in light is not our only window into the foam's potential granularity. While gamma-ray bursts provide one cosmic stopwatch, nature offers an even more extreme and precise probe for testing the very limits of spacetime smoothness. This has led to a fascinating and parallel line of inquiry, one that leverages not the fury of dying stars, but the stable, rhythmic pulses of the universe's most perfect natural clocks. The quest to find a Planck-scale signature shifts from the violent death of massive stars to the steady, reliable spin of distant stellar corpses. But the steady tick of distant pulsars isn't the only way we can search for these spacetime imperfections. The universe has given us an even more direct tool for probing the fabric of reality, gravitational waves. These ripples in spacetime, first predicted by Einstein and finally detected a century later, are caused by the most violent cosmic events like the merging of black holes. They offer a completely new sense with which to perceive the cosmos, and they might be sensitive to the quantum foam in a way that light simply is not. While light travels through spacetime, gravitational waves are vibrations of spacetime itself. They are the medium literally reporting on its own condition, and any graininess or foaminess along their path would leave a telltale signature in the signal we receive. When a gravitational wave passes through an interferometer like LIGO or Virgo, it literally stretches and squeezes the space between the mirrors at the ends of its multi-kilometer-long arms. The precision required to measure this is almost beyond comprehension. LIGO detects changes in length smaller than 1/10,000th the diameter of a proton. This incredible sensitivity makes these instruments potentially capable of sensing something even more subtle, the frothing of spacetime at the Planck scale. As a gravitational wave propagates across billions of light-years, it doesn't travel on a perfectly smooth geometric surface. It traverses the turbulent quantum foam, and that journey could subtly alter the wave itself. One proposed effect is wave dispersion. Much like high-energy light could be slowed by the foam, the different frequencies within a gravitational wave might travel at slightly different speeds. A high-frequency ripple from the final, frantic moments of a black hole merger could arrive out of sync with the lower frequency rumble from earlier in the event, causing the signal to become slightly smeared or distorted. It would be like listening to an orchestra where the piccolos play a fraction of a second behind the cellos, blurring the music. Advanced data analysis techniques are now being developed to search for exactly this kind of frequency-dependent lag in the signals LIGO and Virgo have already captured. Another fascinating possibility is that the foam could introduce a fundamental, irreducible noise into the detectors themselves. This wouldn't be a distortion of a passing wave, but a constant, faint hiss generated by the foam's violent fluctuations happening right here in the laboratory. The seething of virtual black holes and wormholes at the Planck scale would cause the very fabric of space between the mirrors to fluctuate randomly. This would create a minute stochastic jitter in the laser beams, a noise that cannot be shielded against or engineered away because it is a property of spacetime itself. Isolating this signal from the countless other sources of vibration from distant trucks to microscopic cracks in the mirrors, is a monumental challenge, but finding it would be the most direct evidence imaginable that we are living in a quantum gravitational universe. The future of this search lies beyond Earth. The planned space-based observatory LISA will consist of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, connected by lasers. Freed from the seismic noise of our planet, LISA will be sensitive to gravitational waves at much lower frequencies than LIGO, waves generated by the mergers of supermassive black holes. These waves will have traveled across even greater cosmic distances, giving the cumulative effect of the quantum foam more time to imprint upon them. By comparing the pristine, clean signal expected from general relativity with the actual signal LISA receives, scientists hope to see the faint, gritty signature of the foam, finally revealing the true texture of the spacetime we call home. While the search for cosmic signatures of the foam continues, some of the most compelling evidence for its underlying activity comes not from distant galaxies, but from a tabletop experiment right here on Earth. This phenomenon is known as the Casimir effect, and it provides a tantalizing, tangible glimpse into the seething energy of the quantum vacuum, offering a crucial bridge between abstract theory and measurable reality. The setup is deceptively simple. Take 2 perfectly smooth, uncharged metallic plates and place them incredibly close together in a perfect vacuum, separated by a gap smaller than 1/1000th of a millimeter. According to classical physics, in a true void with nothing between them, these plates should just sit there, completely oblivious to one another, but that's not what happens. In reality, the plates experience a faint but unmistakable force pulling them together. This isn't magic, it's a direct physical manifestation of the quantum fluctuations we've been discussing. The empty space between the plates isn't empty at all. It's a turbulent sea of virtual particles. To understand why this attraction occurs, we need to think about the kinds of fluctuations that can exist in the vacuum. Imagine the quantum foam as a chaotic orchestra of every possible note or wavelength. In the wide open space outside the plates, virtual particles of all wavelengths can briefly pop into existence. However, in the narrow gap between the plates, the rules change. The plates act like walls, meaning only certain wavelengths can fit between them specifically, only those wavelengths that are whole number fractions of the gap distance. It's like how only certain musical notes can resonate inside a specific sized organ pipe. The result is that there are fewer possible virtual particle fluctuations happening in the confined space between the plates than there are in the limitless space outside them. This creates a pressure imbalance. The sea of virtual particles on the outside of the plates is more energetic and pushes inward, while the less energetic sea between the plates offers less resistance. This difference in quantum pressure forces the plates together. The Casimir effect is the literal physical force of nothingness pushing on an object. This stunning experiment, first measured definitively in the 1990s, is considered one of the most direct validations of quantum field theory. It proves that the vacuum is not passive, it is dynamic and brimming with energy, but the connection to the quantum foam is even more profound. The foam, with its predicted structure of wormholes and virtual black holes, should influence the spectrum of these vacuum fluctuations. Different models of quantum gravity predict slightly different alterations to the force predicted by standard quantum theory. This has led to a new frontier in experimental physics, precision Casimir measurements. Scientists are now designing increasingly sophisticated experiments using not just parallel plates, but spheres, corrugated surfaces, and materials with different electrical properties. The goal is to measure the Casimir force with such exquisite precision that any tiny deviation from the expected quantum electrodynamics prediction could be a smoking gun. That deviation could reveal the specific texture of the quantum foam, showing whether it's composed of tiny wormholes as some models suggest, or exhibits a different kind of granularity. It's an attempt to feel the grit of spacetime itself by measuring the faintest whisper of a force between two tiny objects in a lab. This brings us to one of the deepest and most philosophical questions in all of science. Why does the quantum world behave so differently from the world we see? At the subatomic level, particles exist in a blur of probabilities, existing in many states at once. Yet, when we look at them, this superposition seems to vanish, collapsing into a single, definite reality. This is the infamous measurement problem, and it has puzzled physicists for a century. How does this collapse happen, and why? One radical theory suggests the answer isn't in the particles themselves, but in the very fabric of spacetime they inhabit. It proposes that the seething chaos of the quantum foam is what constantly performs these measurements, collapsing wave functions and dragging the fuzzy quantum realm into our sharp classical world. The standard interpretation of quantum mechanics, known as the Copenhagen interpretation, simply postulates that observation by a conscious observer causes the wave function to collapse. But this has always been deeply unsatisfying. It places human consciousness at the center of physics and offers no mechanism for how this magical transition occurs. Other ideas, like the many worlds interpretation, suggest the wave function never collapses at all. Instead, the universe splits into countless branches, each realizing a different outcome. While intriguing, this feels like an extravagant solution. What if there's a simpler, more physical process occurring all around us, one that doesn't require conscious observers or infinite realities? This is where the concept of spontaneous collapse enters the picture. Theories like continuous spontaneous localization, or CSL, propose that wave function collapse is not triggered by measurement, but is a fundamental, random process that happens on its own. It's a built-in feature of the universe. A particle in a superposition will spontaneously snap into a definite position after a certain amount of time. For a single electron, this might take millions of years, which is why we can observe quantum weirdness so easily in the lab. But for a larger object composed of trillions upon trillions of atoms, the collapse happens almost instantaneously. This explains why we never see cats, baseballs, or people in quantum superpositions. Their immense size forces them into a single classical state almost immediately. But this theory has a missing ingredient. What is the physical mechanism behind this spontaneous localization? What is actually doing the collapsing? This is the crucial juncture where the quantum foam enters the story as a potential culprit. The foam is not a calm, passive stage. It is a violently fluctuating environment. Imagine trying to balance a perfectly still marble on top of a vibrating speaker. The constant, random jostling would make it impossible for the marble to stay in one precise place for long. Now replace the marble with a quantum wave function and the vibrating speaker with the quantum foam. The relentless fluctuations of spacetime itself, the popping in and out of virtual black holes and wormholes, could provide the physical jostling that constantly nudges quantum systems, kicking them out of their delicate superpositions and into a definite state. In this model, the foam acts as a natural and universal environment that is perpetually measuring the universe. It provides a physical basis for the spontaneous collapse proposed by theories like CSL. The reason quantum effects disappear at larger scales is beautifully explained by this. A large object has so many constituent particles that it is constantly being bombarded by these space-time fluctuations from every direction. This overwhelming noise drowns out any possibility of maintaining a coherent, system-wide quantum state. The foam effectively decoheres the object, forcing it to behave classically. For a single, isolated electron, it can sometimes evade the noise long enough to exhibit weird behavior. But for you or me, the decoherence is total and instantaneous, thanks to the ceaseless churn of the reality we are built upon. This offers a profoundly different way of understanding our place in the cosmos. We are not outside observers causing reality to crystallize by looking at it. We are part of the foam, products of its turbulent activity. The classical world we experience isn't the default state of the universe. It is the emergent result of a constant, invisible interaction between matter and the stormy spacetime it calls home. The quantum foam, in this view, is the great sculptor of reality, tirelessly working to carve the definite from the possible, giving us the stable, predictable world we need to exist. This journey into the quantum foam has taken us from the depths of black holes to the edge of the universe itself, but perhaps the most profound frontier is the one we carry within our own minds. We now arrive at one of the most speculative and hotly debated ideas on our list, the possibility that consciousness itself is not merely a passenger in this quantum universe, but an active participant that interacts with the foamy foundation of reality. This concept, often drawn from interpretations of quantum mechanics, suggests that the act of observation might do more than just collapse a wave function. It could potentially stabilize the turbulent chaos of spacetime itself. The roots of this idea stretch back to the earliest days of quantum theory and the puzzle of the measurement problem. In the famous double-slit experiment, a single electron fired at a barrier with two slits will behave like a wave, passing through both openings simultaneously and creating an interference pattern on the detector screen. This is pure quantum weirdness, but the moment you place a measuring device to determine which slit the electron went through, the wave-like behavior vanishes. The electron acts like a single particle and the interference pattern disappears. The standard Copenhagen interpretation states that the act of observation by a conscious observer is what forces this transition from a blur of possibilities into a single, definite reality. This has led some physicists and philosophers to ponder a staggering implication: that consciousness is not separate from the physical world, but is fundamentally intertwined with its most basic structure. Extending this logic to the quantum foam leads to a radical proposition. If the foam is a realm of infinite superposed possibilities, a constant churn of maybes and what-ifs, then perhaps the presence of a conscious observer acts as an anchor, a stabilizing influence that helps solidify a consistent reality from the chaos. In this view, the universe before the emergence of life was a far more turbulent and indeterminate place, a storm of potentialities with no one to define them. The evolution of conscious beings capable of observation and measurement could have subtly calmed the quantum storm, reinforcing a stable, classical reality simply by perceiving it. It's a concept that borders on the anthropic principle, suggesting that we don't just observe the universe, we help to create it through the very act of looking. This line of thinking is fiercely controversial and is rejected by the majority of physicists who seek a purely physical mechanism for wave function collapse, like the spontaneous localization or environmental decoherence we discussed earlier. They argue that placing consciousness at the center of physics is a form of mysticism that halts scientific inquiry. However, proponents counter that dismissing consciousness entirely is just as unscientific, as it is the one undeniable fact of our existence. They point to the hard problem of consciousness, the question of how and why physical processes in the brain give rise to subjective experience, as evidence that our current physical models are incomplete. They speculate that the answer might lie in a deeper understanding of the quantum world, perhaps even within the dynamics of the foam itself. Could the neural networks of our brains be intricately connected to this Planck scale activity? Some theories, like the Orch or model proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggest that consciousness arises from quantum computations happening within structures inside neurons called microtubules. These quantum processes would be incredibly delicate, shielded from the disruptive noise of the body, and would be directly sensitive to the fundamental geometry of spacetime. In this model, a conscious thought isn't just a classical firing of neurons. It is a symphony of quantum collapses within the brain, each one a minute interaction with the underlying foam. Our stream of awareness would be the continuous process of space-time fluctuations resolving into definite states within our own biology, making our minds not just observers of the foam, but an intimate part of its ongoing expression. While these ideas are captivating, it is crucial to emphasize the vast gulf between fascinating speculation and established science. There is currently no experimental evidence to support the idea that consciousness directly influences quantum systems in the way these theories propose. The brain is a warm, wet, and noisy place, seemingly inhospitable to maintaining the delicate coherence required for large-scale quantum effects. Mainstream neuroscience largely views consciousness as an emergent property of complex classical computation in the neural net, not a quantum phenomenon. Yet the mystery persists and the fundamental question remains: why does the universe appear to require an observer to become fully real? Whether the answer lies in a new physics of the foam, a deeper biology of the brain, or something beyond our current comprehension, the intersection of consciousness and quantum reality remains one of the most tantalizing and unresolved frontiers in our quest to understand the cosmos and our place within it. What if our universe's story isn't a single, linear narrative with one beginning and one end, but is instead an eternal, repeating epic? This is the compelling premise of cyclic cosmology models, which propose that the cosmos undergoes an endless sequence of big bangs, expansions, contractions, and big crunches, only to be reborn again. In such a grand, timeless cycle, the nature of the quantum foam becomes a central character, its properties potentially holding the key to how information, entropy, and even the laws of physics themselves are preserved or reset from one cosmic incarnation to the next. In a single, linear universe model, the quantum foam is often discussed as a static, fundamental feature of reality. But in a cyclic model, its behavior must be far more dynamic. Imagine the universe approaching the Big Crunch, collapsing under its own gravity. As space-time is compressed to unimaginable densities, the quantum foam would be magnified from a microscopic phenomenon to the dominant state of reality. The seething froth of virtual black holes and wormholes would no longer be a subtle background fluctuation. It would become the main event, with the entire cosmos dissolving into a Planck-scale maelstrom of quantum chaos. This isn't just the end of a universe, it's the transformation of reality into its most primordial, foamy state. The critical question for these models is, what happens at the moment of the bounce? This is the hypothesized instant where the collapsing universe, instead of crushing into a singularity of infinite density, rebounds into a new expansion due to some repulsive quantum force. The behavior of the foam at this singularity is everything. One possibility is that the foam acts as a cosmic eraser. The unimaginable energy and turbulence of the bounce could completely scramble and thermalize all the information from the previous cycle. All the structures, the galaxies, the stars, the history of life itself would be dissolved into their fundamental components, their information lost to the chaos. The quantum foam would effectively reset, and the new universe would begin its expansion with a clean slate, its low entropy restored and its arrow of time pointing forward once more. In this view, the foam is the great recycler, ensuring each new cycle begins fresh. However, a more fascinating and complex possibility exists. Perhaps the quantum foam doesn't reset completely. Maybe some fundamental structure or information manages to survive the transition, subtly encoded in the fabric of the rebounding space-time. This idea leans on concepts from loop quantum gravity, which suggests a fundamental granularity to space that prevents a true singularity. If space-time is composed of finite, indivisible quanta, then the collapse can only proceed so far before it meets a kind of quantum repulsion, triggering the bounce. In this scenario, the quantum foam of the previous cycle might not be entirely wiped out. Its configuration, the specific network of spin networks or the particular pattern of fluctuations, could imprint itself on the newborn universe like a cosmic DNA being passed from one generation to the next. This could provide a mechanism for the constants of nature to remain stable across cycles, explaining why our universe has the precise physical laws that allow for complexity and life. This directly tackles one of the biggest challenges for cyclic models, the second law of thermodynamics. In our universe, entropy only increases, creating the irreversible arrow of time. If the universe simply cycled through big bangs and big crunches without some form of reset, entropy would accumulate with each cycle. After an infinite number of cycles, the universe would have reached maximum entropy an eternity ago, and we would not exist in a state of such beautiful structure and low entropy. Therefore, a successful cyclic model must have a mechanism to reset or circumvent this entropy buildup. The quantum foam could be that mechanism. The violent chaos of the bounce might be the universe's ultimate garbage disposal, thermalizing all the accumulated disorder and allowing the next cycle to begin with a new, low-entropy boundary condition. The foam isn't just a feature of space, it's the engine that drives the eternal return, constantly refreshing the cosmos for its next act. Now, let's shift our perspective from timeless cycles to a model that describes the very birth of spacetime from a state of pure connection. This is the captivating idea behind quantum gravity, a theory that suggests the universe didn't begin with a bang, but with a sudden freeze. In this model, the primordial state of reality wasn't a hot, dense point, but an abstract, high-energy network where every single point was directly connected to every other point. This is known as a complete graph, and it represents a phase of existence where the concepts of near and far are completely meaningless because everything is, in a sense, right next to everything else. Imagine the entire universe as a vast, cosmic social network at the moment of its creation. In this network, every single person is immediate friends with every other person in the world simultaneously. There are no degrees of separation, no distant acquaintances, just total, instantaneous connection. In this state, the idea of distance holds no power. You wouldn't need to travel to get anywhere because you're already directly connected to every location. This is the high-energy, hot origin of the quantum gravity model. Spacetime as we know it does not yet exist. There is only a seething, chaotic web of pure relationality. As this fiery network of connections began to expand and cool, a profound phase transition occurred, much like water freezing into ice. The highly connected, chaotic graph began to lose links, connections broke, and the complete graph became a sparse, low-energy structure. It was in this freezing process that the fundamental properties of our universe crystallized. The links that remained stable became the shortest paths between points, and these paths defined what we now experience as distance. The pattern of broken and preserved connections spontaneously generated the dimensionality of space itself, giving us the three spatial dimensions we move through. The quantum foam in this breathtaking picture is the memory of that hot initial state. It represents those residual, flickering connections that continue to pop in and out of existence, the last echoes of a time when everywhere was right here. This model offers a beautiful and intuitive origin for the speed of light. In the hot, completely connected graph, information could propagate instantaneously because every node was linked to every other. There was no speed limit, but as the graph froze and links were lost, information could no longer jump directly from one point to any other. It now had to hop from node to node along the remaining pathways. The maximum speed at which this information can propagate through the sparse graph becomes the cosmic speed limit, the speed of light. The photon is no longer a particle moving through space. It is the manifestation of a signal being passed along this frozen network, its speed dictated by the fundamental connectivity of the graph. The constancy of light speed is therefore a direct relic of this cosmic freezing event, a permanent reminder of the universe's highly connected past. This phase transition perspective also provides a potential new way to think about the problem of time. In the hot, completely connected phase, change is instantaneous and global. The very notion of a sequential order of events may be ill-defined, but as the graph freezes, a local causality emerges. The breaking of links creates a preferred structure, a direction in which information can flow more easily than others, potentially giving rise to the emergent arrow of time we experience. The quantum foam's turbulence, then, could be seen as minor, local reheating events, tiny patches of the graph briefly flashing back to their hot, connected state, allowing for the kind of non-local connections and causal violations that we associate with virtual wormholes and quantum entanglement. In this view, the foam isn't just a seething vacuum. It's the universe remembering and occasionally revisiting its incredibly strange and connected childhood. So far, we've explored theories where the quantum foam is a chaotic froth, a network of information, or a cosmic projection. But what if its turbulence is not a sign of randomness, but a surface-level ripple emerging from a reality of unimaginable depth and order? This brings us to the profoundly philosophical and elegant ideas of physicist David Bohm, whose concept of the implicate order offers a completely different lens through which to view the foam's chaos. Bohm was deeply dissatisfied with the standard interpretation of quantum mechanics, which he felt treated the bizarre behavior of particles as mere mathematical abstraction without an underlying physical reality. He sought a model that was both causally deterministic and deeply interconnected, leading him to propose that the universe we perceive is merely the unfolded or explicate order, a temporary manifestation flowing from a far richer, hidden dimension he called the implicate order. Imagine the universe as a vast, endlessly flowing stream. On the surface, you see ripples, vortices, and bubbles, distinct, separate patterns that form, interact, and vanish. This surface level is our explicate order, the world of separate objects, particles, and events that we directly experience. Now imagine diving beneath the surface. You will discover that all those seemingly independent surface patterns are, in fact, inseparable expressions of the single, unified, flowing body of water. A vortex isn't a thing that exists on its own. It is a temporary, unfolded pattern in the water's continuous movement. For Bohm, this deeper, flowing water is the implicate order. It is an enfolded reality where everything contains and is connected to everything else in a state of undivided wholeness. In this realm, the entire universe is woven into a seamless tapestry, and what we see as separate parts are merely particular aspects that have been momentarily unfolded into our perceptual reality. Now apply this breathtaking concept to the quantum foam. In Bohm's view, the seething frenzy of virtual particles and fluctuating spacetime isn't the fundamental layer of reality. It is the visible surface activity, the explicate manifestation of the constant, dynamic unfolding from the implicate order. The foam's apparent randomness and spontaneity are not due to true chance, but because we are only seeing the surface output of an infinitely complex, deeper process. Each virtual particle popping into existence is not a random fluctuation of nothingness. It is a tiny region of the implicate order momentarily expressing itself into the explicate realm. The foam is the visible signature of reality, constantly refreshing itself from a deeper source, like the flickering pixels on a screen whose true source is the complex software and electricity hidden within the device. This is where Bohm's ideas converge stunningly with the holographic principle we discussed earlier. He proposed that this process of unfolding from the implicate to the explicate order operates in a holographic way. Just as every fragment of a holographic film contains the information for the entire image, every region of space contains a total, enfolded order of the entire universe. The quantum foam in this blended holographic foam model is the dynamic interface where this enfoldment and unfoldment occur. Its fluctuations are not noise, they are the literal texture of reality being computed and projected from a deeper dimensional source. The foam is the grain of the cosmic hologram, and its behavior is governed by the holistic, non-local connections of the implicate whole. This leads to profound philosophical implications that go far beyond physics. Bohm's model suggests that the fundamental nature of the universe is not fragmentation but unity. The separation we experience between ourselves and the world, between the observer and the observed, is an illusion of the explicate order. At the implicate level, consciousness and the physical world are not separate domains. They are different aspects of the same underlying reality. Our process of thought, of observation, might itself be a participatory unfolding from this deeper order. This provides a physical, albeit speculative, basis for the interconnectedness that mystics and philosophers have described for millennia. It suggests that the quantum foam is not just the foundation of space and time, but the active boundary between the manifest world and a far more profound, enfolded reality from which all things emerge. In this view, we are not just observers of the foam, we are dynamic expressions of it, momentarily unfolded patterns in an eternal, flowing whole. This relentless churn of the quantum foam might hold the key to one of the most baffling phenomena in all of science, the spooky connection of quantum entanglement. When two particles become entangled, they form a single, unified quantum state. Measuring one particle instantly influences its partner, no matter how far apart they are, whether across a lab bench or across the galaxy. This spooky action at a distance, as Einstein famously called it, seems to violate the cosmic speed limit set by light, creating the EPR paradox that has puzzled physicists for nearly a century. How can information about a measurement seem to travel faster than light? The quantum foam offers a radical and geometrically beautiful solution. Perhaps these particles aren't truly separate at all. Their instantaneous connection might be facilitated by the foam's turbulent structure, with microscopic wormholes constantly weaving a hidden web of connectivity beneath the smooth surface of spacetime. Imagine two boats floating on a calm ocean. From your perspective on the shore, they appear to be isolated objects separated by a vast expanse of water. But unknown to you, just beneath the surface, a complex network of underwater caves and tunnels connects them directly. A change in one boat causes an immediate effect on the other, not because a signal traveled across the surface, but because they are linked by a hidden, subterranean shortcut. In this analogy, the calm ocean surface is our classical, four-dimensional spacetime. The boats are entangled particles, and the network of underwater tunnels is the quantum foam, teeming with Planck-scale wormholes that provide direct, instantaneous connections between points that seem far apart in our conventional reality. The correlation isn't spooky, it's simply topological. The particles are, in a very real geometric sense, right next to each other through a hidden fifth dimension woven by the foam. This idea, often called the ER equals EPR conjecture, was powerfully advanced by physicists Juan Maldaisner and Leonard Susskind. The name itself is a fusion of two landmark ideas in physics. Refers to the Einstein-Rosen bridge, which is the formal term for a wormhole, a shortcut through spacetime. EPR refers to the Einstein-Podolsky-Rosen paradox, which describes the troubling non-locality of entanglement. The conjecture boldly proposes that these two concepts are not just related, they are two different descriptions of the same underlying phenomenon. Every pair of entangled particles is connected by a microscopic wormhole, a thread of the quantum foam so tiny it's unstable and fleeting, but real nonetheless. When you entangle two particles, you are, in effect, quantumly stitching a tiny wormhole between them. Measuring one particle doesn't send a signal. It changes the geometry of this microscopic bridge, instantly affecting its partner. This provides a breathtakingly elegant resolution to the EPR paradox. The instantaneous correlation doesn't violate the speed of light because no information is actually traveling through space. The connection is already there, baked into the fabric of reality through these wormhole links. It's a geometric rather than a communicative solution. The paradox vanishes when we realize that our perception of distance is an illusion, a large-scale approximation that breaks down at the Planck scale. The universe, at its most fundamental level, is a vast, intricate network of these non-local connections, a cosmic fabric woven together by the foam's invisible threads. What we perceive as empty space separating objects is actually filled with a dense, dynamic tapestry of microscopic bridges, ensuring that everything is, in some way, connected to everything else. The implications of this extend far beyond a simple pair of particles. It suggests that the quantum foam is the substrate of cosmic unity. The entanglement that seems so strange in the lab might be the default state of the universe at its birth. During the Big Bang, everything was in such intimate contact that it was all entangled. As the universe expanded, the distances between objects grew astronomically, but these primordial quantum connections, maintained by the foam's wormhole network, never truly broke. We may still be subtly entangled with the most distant galaxies, all part of a single, non-local whole that is constantly refreshed and renewed by the seething activity at the foundation of reality. The foam doesn't just allow for non-locality, it is the physical manifestation of the universe's deep, invisible interconnectedness. But if the nature of the quantum foam is so deeply woven into the laws of physics, a profound and unsettling question arises. Why does it have the specific properties that allow for our existence? This leads us to a theory that is less about the mechanics of the foam and more about the philosophical context of our entire reality. It's the anthropic principle, and it offers a startlingly simple, yet deeply controversial, explanation for why we observe a universe that is, for the most part, smooth and stable. The argument suggests that the parameters of the quantum foam are not random. They are precisely tuned within a narrow window of possibility to allow for the emergence of conscious life. We are not passive observers of the foam's properties. Our very presence is a filter that selects for them. To grasp this, imagine a universe where the quantum foam was far more violent. Instead of gentle Planck-scale fluctuations, the froth features macroscopic wormholes and virtual black holes the size of marbles or even mountains. In such a reality, the very concept of a stable object would be impossible. Atoms could not form, as the intense gravitational tides of a popping virtual black hole would instantly rip electrons from their nuclei. Molecules would never assemble. The fabric of spacetime would be so turbulent that time itself might lose all consistent direction, with cause and effect hopelessly scrambled. In this chaotic nightmare, the universe would be a formless, seething maelstrom, utterly incapable of supporting any structure, let alone the incredible complexity of a living cell. It would be a cosmos without observers, without anyone to marvel at its laws or curse its chaos. Now consider the opposite extreme, a universe where the quantum foam is completely absent. Spacetime is perfectly smooth and classical, all the way down to infinitely small scales. While this might sound ideal, it presents a different catastrophe. Without the energy of quantum fluctuations fueling the vacuum, phenomena like the Casimir effect would vanish. More critically, the process of cosmic inflation, which relies on quantum fluctuations to seed the formation of galaxies, might never have gotten started. The universe could remain a vast, empty, and perfectly uniform void, forever cold and dark. Without the initial wrinkles provided by the foam, there would be no gravitational seeds, no stars, no planets, and again, no life. A universe that is too smooth is just as sterile as one that is too chaotic. We find ourselves, therefore, in a Goldilocks universe where the quantum foam is neither too hot nor too cold, but just right. Its fluctuations are violent enough to have sparked the formation of everything we see, yet gentle enough to allow that structures to persist for billions of years. The anthropic principle argues that this is not a miraculous coincidence. In a vast multiverse, perhaps one driven by eternal inflation, where countless universes bubble into existence, each with its own random set of physical constants and foam properties, Only the rare universes where the foam's parameters fall within this incredibly narrow window will ever give rise to observers who can wonder about it. We do not observe a wildly foamy universe or a perfectly smooth one because such universes are, by their very nature, lifeless and empty. Our existence as conscious beings capable of measuring the foam acts as a selection filter, ensuring that the only universe we can possibly find ourselves in is one whose underlying quantum nature is compatible with our own complexity. This perspective can feel like a cop-out to some, a way of avoiding the deeper question of why these parameters are life-friendly. Yet it provides a powerful framework for understanding the apparent fine-tuning we see not just in the quantum foam, but in countless other fundamental constants, from the strength of gravity to the mass of the electron. It shifts the question from "why is the universe like this?" to "what must the universe be like for us to be here to ask the question?" The quantum foam, in this view, is not a static feature of reality but a variable one, and our observation of its gentle nature is the ultimate testament to the delicate and precise conditions required to turn a chaotic vacuum into a home. But what if our foundational theory of gravity itself is incomplete? For decades, most quantum gravity research has operated under the assumption that Einstein's general relativity is the correct classical theory to be quantized. Yet, a persistent anomaly in the cosmos has led some scientists to propose radical alternatives. The observed rotation curves of galaxies, the way stars on the outer edges move just as fast as those near the center, defy predictions based on the visible matter present. The mainstream solution is dark matter, an invisible, mysterious substance that provides the extra gravitational pull. However, a small but dedicated group of physicists champions a different approach, modifying the laws of gravity themselves. Theories like MUND, which stands for Modified Newtonian Dynamics, and its relativistic extension, TVS, or Tensor Vector Scalar Gravity, propose that on very large galactic scales, gravity behaves differently than either Newton or Einstein predicted. This raises a fascinating and often overlooked question. If gravity itself is different, what does that imply for the quantum foam that is supposed to be its microscopic embodiment? In the general relativity picture we've explored, the quantum foam's wild fluctuations are a direct result of applying quantum principles to Einstein's equations. The foam's character, its predicted wormholes, virtual black holes, and non-commutative geometry is sculpted by the specific mathematical shape of those equations. Now, imagine an alternative theory of gravity that has a different mathematical structure. It might lack the specific nonlinearities that make Einstein's equations so prone to producing singularities and violent quantum fluctuations. A modified gravity theory could, in principle, predict a much calmer, less turbulent vacuum at the Planck scale. The foam might not be a frothing sea, but a gentle mist. Instead of a constant fireworks display of virtual black holes, the quantum vacuum in a MUND-like universe might be dominated by far less extreme, and perhaps far less disruptive, geometric fluctuations. The very foaminess of spacetime could be a direct signature of which classical theory of gravity is correct. This opens up a new, potential testing ground for these competing theories. While MUND and its cousins were designed to explain galactic-scale dynamics without dark matter, their implications would ripple all the way down to the smallest possible scales. If we could find a way to probe the quantum foam and measure its roughness, we might be able to test general relativity against its alternatives in a domain completely separate from astronomy. For instance, the predicted time lag for high-energy photons traveling across the universe, which we discussed earlier, is calculated using standard quantum field theory in a general relativistic spacetime. A modified gravity theory would lead to a different calculation, potentially predicting a smaller delay, or perhaps no delay at all. A precise null result from future gamma-ray burst or neutrino observatories could therefore be evidence not just for a smoother foam, but for an entirely different formulation of gravity. The challenge, of course, is that constructing a complete and consistent theory of quantum gravity is difficult enough with Einstein's equations. Doing so for a modified gravity theory is a monumental task that remains largely unexplored. TVS, for example, introduces additional fields, a vector and a scalar field alongside the standard tensor field of spacetime metric to mediate gravity. Quantizing this more complex system could lead to a foam that isn't just smoother or rougher, but qualitatively different in nature. Perhaps its fluctuations are correlated in a new way, or maybe the additional fields interact with the geometry to suppress the formation of virtual black holes. The holographic principle might take on a different form, or the entanglement of spacetime itself could be governed by new rules. Exploring these possibilities is a wide open frontier, offering a parallel path to understanding quantum gravity that doesn't start from the assumption that dark matter exists. It forces us to ask not just what the quantum foam is, but what it could have been under different physical laws, reminding us that the universe's foundational texture might be more flexible and more deeply connected to the large-scale cosmos than we ever imagined. To truly appreciate the quantum foam, we must trace its conceptual roots back to the very framework that first revealed the hidden turmoil of the vacuum, quantum field theory. This pillar of modern physics doesn't treat particles as tiny, solitary marbles, but as localized excitations in omnipresent, underlying fields that fill all of spacetime. The electron field, the electromagnetic field, the quark field, each of these is a kind of invisible canvas stretching throughout the universe. A particle is simply a place where this canvas is vibrating in a specific, quantized way. This elegant shift in perspective from particles to fields was one of the most profound breakthroughs in science, but it came with a bizarre and unavoidable consequence. The concept of a true vacuum, a state of perfect emptiness, had to be permanently retired. In quantum field theory, even at its absolute lowest possible energy state, a field can never be completely still. Due to the Heisenberg uncertainty principle, its value is always fluctuating. It's like a pendulum that can never quite come to rest at the very bottom of its swing. It always has a tiny, irreducible jitter. This means that what we call empty space is actually a seething soup of these fluctuations. For a brief, fleeting moment, a fluctuation in, say, the electron field can borrow enough energy to create a virtual electron and its antimatter partner, a positron. These virtual particle pairs are not mere mathematical abstractions. Their effects have been conclusively measured in the lab, most famously in the Casimir effect. They pop into existence, violate energy conservation for an imperceptibly short time, and then annihilate each other, returning the energy they borrowed. This endless, frantic dance of creation and destruction is the true nature of the vacuum. Now, let's bring gravity into the picture. In our previous theories, we explored how gravity warps the stage of spacetime. Quantum field theory shows us that this stage is already alive with a frenzy of energy fluctuations. John Wheeler's genius was to ask, what happens when these two ideas collide? If energy tells spacetime how to curve, and the quantum vacuum is brimming with energy, then the vacuum fluctuations must be warping the fabric of the universe itself at the smallest possible scales. The quantum foam is the gravitational manifestation of quantum field theory's vacuum fluctuations. The virtual particle pairs are no longer just appearing and disappearing on a static, smooth background. Their immense energy is actively twisting and knotting the spacetime they inhabit, creating the turbulent landscape of microscopic wormholes and virtual black holes that we call the foam. It's a feedback loop of pure chaos. The fields fluctuate, which warps spacetime, and that warped spacetime in turn influences how the fields can fluctuate. This synthesis creates a monumental problem for physicists, one so severe it has halted progress for decades: the problem of renormalization. Quantum field theory is famously plagued by infinities. When you calculate the probability of certain particle interactions, the equations often spit out an answer of infinity, which is physically meaningless. Thankfully, for the three other fundamental forces, electromagnetism, and the strong and weak nuclear forces, physicists developed an ingenious mathematical procedure called renormalization to sweep these infinities under the rug. It involves carefully redefining certain measurable parameters, like a particle's mass and charge, to absorb the infinite quantities, leaving behind finite, exquisitely accurate results that agree perfectly with experiment. But gravity stubbornly resists this fix. The problem is that in general relativity, energy and mass are the sources of spacetime curvature. The vacuum fluctuations have a truly enormous energy density, and when you try to calculate their gravitational effect, the infinities that appear are far more vicious and unmanageable. You can't simply redefine a few parameters to make them go away. The entire geometric structure of spacetime itself becomes divergent. Renormalization works for the other forces because they operate on a fixed spacetime stage. Gravity is the stage. Trying to renormalize gravity is like trying to fix a corrupted computer file, while the very operating system needed to run the repair program is itself the corrupted file. The infinities are a screaming signal that our two most successful theories, when combined, are fundamentally incompatible at these extreme scales. The quantum foam, therefore, represents more than just a curious phenomenon. It is the physical embodiment of this deepest conflict in physics, the chaotic no-man's land where our understanding of the universe finally breaks down. This chaotic churn holds the key to what many consider the most severe crisis in fundamental physics, the black hole information paradox. The problem strikes at the very heart of quantum mechanics, challenging a sacred principle called unitarity, the idea that information, the distinct identity of every particle and its state, can never be truly lost. If you burn a book, its information isn't gone. It's just transformed into smoke and ash, theoretically recoverable if you could track every single particle. Quantum mechanics insists the universe always preserves this information, keeping a perfect cosmic ledger. But black holes, with their immense gravity and mysterious interiors, seem to offer a way to break this rule, to permanently erase information from the universe. The paradox was sharpened by Stephen Hawking's own discovery. He showed that black holes aren't completely black, they slowly evaporate by emitting a faint glow of radiation. This Hawking radiation, however, appears to be completely random, a featureless thermal noise determined only by the black hole's mass, charge, and spin. It carries no imprint, no fingerprint of the specific material that originally fell in. If a library falls into a black hole, the Hawking radiation that eventually comes out as the black hole evaporates seems to be just hot gas, with no trace of the information about every book, every word, every letter that was consumed. Once the black hole vanishes entirely, that information appears to have been deleted from reality, a direct violation of quantum law. This is where the quantum foam offers a breathtakingly elegant escape route. The traditional view pictured information traveling unimpeded into the black hole's central singularity, where it would be crushed out of existence. But if spacetime is fundamentally foamy, that simple journey is impossible. The path to the singularity is not a smooth, clean highway. It's a turbulent, chaotic obstacle course riddled with microscopic wormholes and virtual black holes. As information, whether it's a particle or the entire library, approaches the event horizon, it wouldn't simply plunge inward. It would be violently scrambled and disseminated by the frothing spacetime foam. The information wouldn't be destroyed. It would be quantum mechanically tangled with the very structure of the horizon itself. Imagine trying to follow a single drop of ink falling into a raging whirlpool. You wouldn't be able to track it to a single point at the bottom. Instead, the turbulent currents would instantly smear the ink throughout the entire vortex, dyeing the water itself. In this analogy, the whirlpool is the black hole's event horizon, and the churning water is the quantum foam. The information from the infalling matter doesn't travel to a central point. it gets smeared across the entire horizon, its bits encoded into the frenetic fluctuations of the foam. The event horizon, therefore, isn't just a passive boundary. It becomes an active, dynamic membrane, a super-dense, chaotic computer that is constantly processing and encoding information. This resolves the paradox by providing a mechanism for the information to escape. As the black hole evaporates via Hawking radiation, each particle that radiates away is not random. It carries away a tiny piece of that scrambled information, slowly decoding the message that was imprinted on the horizon's foam. The radiation only appears random and thermal to an observer who doesn't have the full picture. To an observer who could somehow collect all the Hawking radiation over the black hole's entire multi-billion-year lifespan, it would contain the complete and recoverable story of everything that ever fell in. The information was never truly inside the black hole. It was always on the surface, being slowly revealed particle by particle. The foam provides the physical substrate for this process, its endless fluctuations acting as the medium that stores and processes the data, ensuring the universe's ledger remains perfectly balanced and unitarity is preserved. Now, let's turn our attention to one of the most mind-bending states of matter ever conceived, a structure that challenges our very definition of what matter is by breaking a fundamental symmetry of time itself. These are time crystals, and their potential connection to the quantum foam opens a portal to a reality where the fabric of spacetime might not just be turbulent, but rhythmically, perpetually ticking. Unlike all other phases of matter, which are defined by their arrangement in space, think of the repeating lattice of atoms in a diamond. A time crystal's most defining order exists not in space, but in time. It's a system that, when nudged, doesn't just react and settle back down. Instead, it enters a perpetual cycle of motion, oscillating at a regular beat without ever consuming energy to do so. This isn't a perpetual motion machine. It's a quantum system locked in a ground state that nonetheless exhibits periodic motion, a kind of cosmic clock that winds itself. The connection to the quantum foam lies in this concept of broken symmetry and perpetual oscillation. The foam, as we've pictured it, is a seething, chaotic mess. But what if within that chaos there is a hidden order, a subtle, rhythmic pattern to the fluctuations? The formation of a time crystal requires a system to spontaneously break time translation symmetry. This means that while the laws of physics are the same at every moment in time, the symmetry, the ground state of the system itself is not. It changes periodically, ticking from one state to another and back again. If the quantum foam possesses any form of inherent periodicity or resonant frequency at the Planck scale, it could provide the perfect, turbulent substrate from which these bizarre temporal structures could emerge. The foam wouldn't just be a random noise generator. It could be a drummer keeping a faint but fundamental beat for the universe. Imagine the vacuum not as a formless static, but as an ocean with a deeply embedded rhythmic tide. On the surface, you see chaotic waves, the unpredictable popping of virtual particles and wormholes. But beneath that surface turbulence, there's a powerful, regular pulse. This underlying rhythm could potentially influence matter that interacts with it. If you could create a quantum system that is sensitive enough, that pulse could nudge it into synchrony, forcing it to oscillate in time with the universe's own hidden metronome. The time crystal would then be a kind of harmonic resonator, its stable, periodic motion a direct echo of the temporal structure woven into the foam itself. It would be evidence that the universe's most fundamental level has a preferred clock cycle, a natural frequency of existence. This isn't just theoretical poetry. It provides a potential physical mechanism for how time crystals can exist as stable, ground-state objects. Their oscillation doesn't need an external driver because the drive is internal. It's baked into the very spacetime they inhabit. The quantum foam's rhythmic fluctuations would constantly provide the tiny kicks needed to maintain the crystal's motion without ever allowing it to dissipate its energy and stop. The time crystal becomes a visible, measurable manifestation of the foam's hidden temporal order, a bridge between the abstract froth of Planck scale physics and the strange, new phases of matter we are only beginning to create in laboratories here on Earth. We've journeyed through 29 extraordinary theories, from holographic projections to temporal crystals, each painting a radical new picture of reality's foundation. But where do we go from here? How do we move from breathtaking speculation to concrete evidence? This brings us to our final theory, a look at the future of quantum foam research, where scientists are building unimaginably precise experiments and harnessing the power of new technologies to finally feel the texture of spacetime itself. One of the most promising frontiers doesn't require a particle accelerator the size of a solar system, but rather a new type of computer. Researchers are now using quantum computers to simulate the fabric of spacetime. The logic is brilliant. If a quantum computer operates on the same principles of superposition and entanglement that are thought to govern the quantum foam, then we can program it to act as a miniature model of spacetime itself. By carefully encoding the rules of a quantum gravity theory, like loop quantum gravity or a holographic boundary, into the qubits of a quantum processor, scientists can watch the simulation unfold. They can see if the complex, chaotic interactions between qubits spontaneously generate a stable, four-dimensional structure, just as causal dynamical triangulations predicted in its digital simulations. It's like building a tiny, working model of a hurricane in a lab to understand the physics of storms. These quantum simulations won't create actual spacetime, of course, but they could reveal which mathematical models naturally produce a universe that looks like ours, guiding us toward the correct theory of quantum gravity. Meanwhile, back in the classical world, tabletop experiments are achieving levels of sensitivity that were pure fantasy just a decade ago. The goal here is to detect the faintest possible whispers of the foam's activity. One ingenious approach involves micro-mechanical oscillators, tiny, vibrating paddles cooled to near absolute zero. At these cryogenic temperatures, quantum effects become dominant. The idea is to isolate one of these oscillators from all other vibrations and watch it with laser light of incredible precision. If the quantum foam is truly a turbulent sea of fluctuations, it should impart a tiny, fundamental jitter to the oscillator, a minuscule shaking that cannot be eliminated no matter how perfectly you isolate it. This would be the signature of spacetime itself trembling. Detecting this would be like feeling the individual raindrops in a storm by watching a single leaf quiver. Another approach uses ultra-precise atomic clocks. If the foam causes light to slow down slightly, it should also cause subtle fluctuations in the perceived flow of time. By comparing two of the world's most accurate clocks, scientists could look for a faint, synchronized drift, a telltale sign that time itself is stuttering due to the foam's granularity. The search doesn't end on Earth. The next great leap will come from space-based observatories free from the seismic and thermal noise of our planet. The Laser Interferometer Space Antenna, or LISA, is a monumental mission planned by the European Space Agency. It consists of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, connected by lasers. This giant interferometer in the vacuum of space will be exquisitely sensitive to low-frequency gravitational waves from merging supermassive black holes. As these waves travel for billions of years to reach us, the cumulative effect of the quantum foam could subtly distort them. LISA could detect a frequency-dependent scattering or a faint, stochastic noise woven into the signal, the literal hum of spacetime's granular structure. Furthermore, missions like the proposed gamma-ray burst ultraviolet optical telescope for LISA would provide simultaneous observations of the light from these events, creating the ultimate cosmic stopwatch to test for any energy-dependent speed variations in photons, a direct probe of the foam's roughness. The path ahead is one of convergence where quantum computing, nanoscale engineering, and space-based astronomy will work in concert to illuminate the darkest corner of physics. We are no longer just theorizing about the quantum foam. We are building the tools to touch it. Each null result, each experiment that finds nothing, tightens the constraints, forcing our theories to become more elegant and precise. And one day, perhaps in this decade or the next, one of these experiments will return a signal. It might be a faint jitter in a microscopic paddle, an anomalous lag in a gamma-ray burst, or a strange noise in a gravitational wave. It will be the data point that doesn't fit, the whisper from the void that says our smooth reality is an illusion, and that beneath it all, the universe is buzzing, churning, and alive with a quantum energy we are just beginning to perceive. From Wheeler's initial vision of a seething, turbulent geometry to the holographic principle's suggestion that our entire reality is a projection from a distant, two-dimensional surface, the range of ideas about quantum foam is as vast as the cosmos itself. We've journeyed through a landscape where spacetime is built from tiny, triangular pieces, woven from a spin network of information, or even generated by a cosmic freeze from a state of pure connection. We've seen how this foam might be the engine behind dark energy, the sculptor of time's arrow, and the key to resolving the black hole information paradox. Some theories propose it's a timeless chaos, while others suggest it might even hold a hidden rhythm, like in the concept of time crystals. This incredible diversity isn't a sign of confusion, but a testament to the vibrant, creative struggle to understand the deepest foundation of our reality. What makes this field so electrifying is that it remains wide open. There is no single accepted theory yet, no textbook answer to what spacetime is like at the Planck scale. This isn't a finished story, it's a live, ongoing investigation happening at the very frontier of human knowledge. Each of these 30 theories represents a different path toward the same ultimate goal, a complete theory of quantum gravity. The quantum foam is the central mystery that every approach must confront, the chaotic heart of the problem that could ultimately unlock a new understanding of the universe, unifying the very large with the very small into one elegant framework. This journey doesn't end here. New experiments are coming online all the time, from ever more sensitive tabletop detectors feeling for the foam's jitter to space-based observatories like LISA that will listen for its hum in gravitational waves. Quantum computers are being programmed to simulate spacetime itself, offering a digital window into this mysterious realm. Every day, physicists are pushing the boundaries, using both mathematics and technology to try and feel the texture of nothingness. Your mind is the most important tool in this endeavor because it is the curious human spirit that drives this quest for understanding, so we want to hear from you. Which of these wild theories resonated the most? Was it the holographic universe, the idea of microscopic wormholes connecting everything, or something else entirely? Let us know your favorite in the comments below, and be sure to subscribe so you don't miss our next deep dive into the cosmos's greatest mysteries. The universe is stranger than we can imagine, and together we're just beginning to explore